Hello and welcome to the introduction video to experiment 4, the IR spectroscopy of small molecules. In this experiment, we'll be talking about the infrared region of energy, and that's the energy region just slightly lower in energy than the visible spectrum, or the visible region. Ultraviolet light is even higher in energy than the visible region, X-rays, gamma rays. Of course, this is our high energy side. The high energy form of the electromagnetic spectrum contains enough energy to allow atoms to undergo nuclear transitions. In the visible and ultraviolet region, there's enough energy contained within a photon of light to cause molecules or atoms to undergo electronic transitions. The infrared region is just right to allow molecules to absorb energy through vibrations. Even lower in energy would be the microwave region. And this wavelength is suitable for allowing molecules to change their rotational energy. And then even lower energy forms of radiation, radio waves, can cause electrons to flip their spins, nuclear to flip their spins, and you may think of this region as being responsible for the nuclear magnetic resonance form of spectroscopy. So of course, some of the key equations we'll be working with are E is equal to h nu, Planck's equation, of course, E is equal to hc over lambda to relate the frequency or the wavelength to the energy of a given photon. So one of the ideas of this experiment is we can take electromagnetic radiation, pass it through a sample, obtain a spectrum where we can see what wavelengths of light were absorbed by the sample. And in this experiment, we'll just have this light source be an infrared light source and our sample be generally a gas phase sample, and then we'll get a spectrum of the different sort of changes that are undergoing the molecule through the absorption of that light. Now you can see here in this figure below that this would be the energy that you might think of being changed to the absorption of a visible or an ultraviolet photon of light, because we see the changes being a change in electronic state. Within this experiment, we're going to see through the absorption of infrared light changes undergoing just within the first one or two vibrational energy levels of our molecules. So we're going to see the changes to and from different vibrational states to other vibrational states. So we're going to see just transitions between these different vibrational states. Okay, so this is actually what the infrared spectrum of HCl looks like. In our experiment, we'll get a higher resolution spectrum than the one you see here, but what you kind of see is almost like two branches of the spectrum for a molecule of HCl. Now, one thing that's important to note here is that this is a gaseous sample, so this really isn't hydrochloric acid, H plus, Cl minus, and water. This is a gas phase sample where we have a single bond between the H and the Cl, and so we have a diatomic molecule. Now, you may have expected, if I had asked a question, what would you think the infrared spectrum would look like for something like HCl? You may have predicted just sort of a single peak, because it has one bond. Why would it have more than one peak? Well, what we're seeing here within HCl is a more refined structure that we're getting from the absorption of light from a particular vibrational and rotational state through an allowed transition to some other vibrational and rotational state. What we're going to see is that we get two different branches of our spectrum that emerge due to our ability with this small molecule in the gas phase to resolve the individual transitions from particular vibrational rotational states to other vibrational rotational states. So you can imagine probably one of the most stable states or the most stable state would have a vibrational quantum number of 0 and a rotational quantum number of 0. So we'll see that V is a vibrational quantum number, J is the rotational quantum number. So you would probably imagine the most stable state, the lowest energy state, would be V equals 0, J equals 0. Now, you can imagine within this ground vibrational energy level, you can have other rotational states, because our rotational quantum number has integral values, 0 and up. Same thing with our vibrational quantum numbers. It has the same quantum behavior where we can have vibrational quantum numbers of 0, 1, 2, etc., but not anything other than those whole numbers. And so you can imagine that if you have a series of rotational states that are occupied at say, room temperature for a given sample, and that these are exciting to some higher energy state, say from V equals 0 to V equals 1, if they're also undergoing a change in rotational quantum number, then those rotational energy levels, let's imagine they all have a slight difference of energy, associated with them, then you can probably imagine the emergence of this band structure. And so then another thing you might see here is if we imagine j equals 0, 1, 2, 3, something interesting happens that we'll take a look at a little bit later today within the first day of experiment 4. But one of the things we'll get a sense of is that it's probably around j of 2 to 3 for something like HCl that's actually most occupied by a sample at room temperature. So it might seem kind of fascinating at first that if you have a room temperature sample of a gas phase compound, that the most occupied state turns out not to be V equals 0, J equals 0. V equals 0, J equals 0 is the most stable, it's the lowest energy state, but it turns out not to be the most occupied state. You'll see some higher J value here being the most occupied rotational energy level at room temperature. And so what we're going to see is kind of a snapshot, and really what we're seeing here is a snapshot of which of these rotational energy levels are actually occupied with an observable population at room temperature. Now, in some ways, I might be getting ahead of ourselves if you haven't seen much about the rigid rotor model that describes the rotational energy levels, and then the harmonic oscillator model that describes the spacings of the vibrational energy levels, and then some anharmonic models that kind of allow there to be some true behavior of bonds described through those models, then this may all seem foreign to you at this point, but we'll try to make sense of it, sense of those models as we go along here. Okay, so one of the important equations of physical chemistry or chemistry in general is the Schrodinger equation, H psi is equal to E psi. So you have a Hamiltonian operator, operates on a wave function, returns the energy of that wave function. And one of the things we might try to do is approximate the wave function as having a term from the electronic energy, the vibrational energy, and the rotational energy, so that you can approximate the energy of your molecule as being a sum of the electronic state the molecule exists in, the vibrational state, and the rotational state. Now, it's important to recognize that this is actually an approximation, to think that these three terms are all separable. But if we use this as an approximation to kind of begin, it allows us to kind of get a sense of thinking of the molecule as having, okay, let's consider the changes of from the vibrational changes of energy, and then the changes from the changes in the rotational energy. And then if we're just simply having a molecule undergo a change of energy through the absorption of visible light, presumably we're not going to have enough energy present to change electronic state. So within the absorption of infrared light, we're not going to change the electronic energy, but rather just change the vibrational and rotational energy levels. And so the harmonic oscillator model is a model you may recall from just physics class. You may have seen it also in Chem 4300. If you're in that class now and you haven't seen this yet, hopefully this is just a quick little introduction that can help you understand that model when you get to it. Same thing if you're in the physical biochemistry sequence, you may not see this until the second semester. So if you're just in the first semester, it may be a while before you see this, but hopefully this section here will give you a little bit of a introduction to that topic when you get to it in class. But our vibrational energy level from our harmonic oscillator model is found to be quantized with energy with quantized energy levels of h nu v plus a half. And so one of the important things here is seeing that we have a symbol nu, the Greek letter nu, and then that's that corresponds to the fundamental vibrational frequency. Let's talk units in just 1 second. And then V is the vibrational quantum number. This is the one that has whole number values here. So it's important to notice that we have an equation that has two similar symbols in it, but one of them is V, the vibrational quantum number, whole number value 0 and up. And then nu is the fundamental vibrational frequency that gives us the vibrational, or gives us the energy as a function of that vibrational quantum number. So if you think of energy as a function of V, so our ground state, first highest, second highest, third highest, etc., from the harmonic oscillator model. So the harmonic oscillator model just treats two masses, M1, M2 on a spring, and the masses are simply vibrating with the energy equal to h nu v plus a half. Now, if we're going to get units of energy out, of course, Planck's constant has units of joules times seconds. So V here, or excuse me, nu, the fundamental vibrational frequency, has units of inverse seconds. So you can multiply that by joules times seconds, the units of Planck's constant, and return an energy value in units of joules. Now, if you're thinking of energies as we start to do some calculations with these quantities, this is going to be a really small number because this is going to correspond to the energy of a single molecule of HCl. So you're going to think of these energies as being, in the order of, 10 to the minus 20 to 21 joules for a single molecule. Now, nu, the fundamental vibrational frequency, So the fundamental vibrational frequency, units inverse seconds, is related to two properties of the bond. One of them is the force constant K, and then mu is the reduced mass. So reduced mass is simply the sum of the two masses of the bond divided, or it's the product of the masses divided by the sum of the masses. So that's our reduced mass mu. So we got nu, mu, and v, similar sounding in terms of mu and nu, and then similar looking in terms of v and nu, but completely different in terms of what they're representing. So the reduced mass relates then to the force constant. The force constant, usually we think of this as being newtons per meter. A force constant has units of force per unit meter. So the Newton is the SI unit of force. So force is mass times acceleration. And so if you divide this by meters, so newtons divided by meters is really just kilograms seconds to the -2. So you got kilograms to the per second squared, and then you have that divided by the reduced mass. So your masses here, as you start to think of calculations, think of one single molecule. So you're thinking, okay, maybe I have a 1H and a 35 Cl. So you're thinking the precise atomic mass of 1H and 35 Cl. Looking up those precise masses, perhaps in the NIST web book, perhaps CRC, maybe just Wikipedia, but wherever you can get those accurate masses, you might think of putting the mass 1 times mass 2. I think of those masses as being in kilograms. Of course, it's going to be really small because you're talking about the mass of one single atom. So you might have to take the mass in AMU. So you may have a mass of about 1 AMU. Look, as you start doing calculations, look that up more precisely, but then the number of AMU is an Avogadro's number of AMU per kilogram per gram, and then you can go gram to kilogram from there. So 1 AMU. Sorry, my handwriting is not great, but Avogadro's number of AMU in 1 gram is our conversion over to the gram scale, and of course 1,000 grams. And a kilogram gets you up to the kilogram scale. So we're talking 10 to the minus 26 to 27 is sort of the number of kilograms that a given atom has. So a really small mass, but yet the unit of the reduced mass is kilograms. So if you're thinking of the units, how they relate here to force constant, the reduced mass to the frequency, imagine you take your force constant units, kilograms per second squared, divide that by the units of the reduced mass, kilograms, and then ultimately you're taking the square root. Taking the square root of inverse second squares gives you inverse seconds. So the relationship between your frequency, force constant, reduced mass is given with this equation here. And then we have one other term that you might use is the vibrational energy, but in units of wave numbers or some inverse length scale. Usually when we think of vibrational frequencies, we're thinking those in units of inverse centimeters. And so we can convert to a harmonic frequency, but in units of wave numbers or some inverse length by simply dividing by our energy by Hc. Okay, so this just becomes a matter of how do you take a energy and then relate that to the wavelength, and then if you want to invert the wavelength, then that would be the inverse length scale. And so the if you just simply take your energy divided by Hc, then that's equal to 1 over lambda. So 1 over the wavelength is equal to the energy divided by Hc. And so just take the energy, h nu, divide by Hc, gives you now your frequency. Instead of your frequency in inverse seconds, it gives you a frequency in centimeters. So this gives you a relationship to the vibrational energy in terms of the vibrational frequency wave numbers to the vibrational quantum number V. So what this equation here is saying is that your vibrational energy in wave numbers is equal to the harmonic frequency inverse seconds, or inverse centimeters, V plus a half still. So our IR selection rule is that the vibrational quantum number has to change by 1, and we're starting in 0, so it can't go to -1, so the vibrational quantum number can change up by 1, and that's going to be our most intense absorbance that we see is going to be V equals 0 to 1. The overtones are observable for real molecules. So if we compare our harmonic potential, you can sort of look at the Morse potential. A Morse potential is a better description of maybe something like HCl or a real molecule where the bond can actually break. A spring model, the spring will never break, but for a real bond, we have to allow the bond to break at infinite separation. So as we're moving to the hydrogen atom plus the chlorine atom, eventually the energy asymptotes. The Morse potential helps us see that the actual vibrational energy levels are a little bit lower than where we actually predicted them with the harmonic model. So you see the 0 to 1, 1 to 2, 1 to 3 prediction for the harmonic model is a slight over approximation, and we can correct the approximation using the Morse potential, or understand that those energy levels are going to be they're going to be higher in energy than we expect for a real molecule. Now, there's an anharmonic correction that we could make to say, well, what if we try to correct our harmonic frequency with what we might call the anharmonic, or the first anharmonic correction? That's omega E xe, v plus a half squared. And then we can do it a second time. We have the second correction to the harmonic frequency. These are sort of introducing, if you imagine a harmonic potential, imagine adding cubic functions, imagine adding quartic functions, imagine maybe as well, this is like a Taylor series expansion of the error introduced in this approximation. But the key is you just end up with an equation that relates to terms that are now of a higher order that allow us to describe or more accurately predict the energy levels in a real molecule. So the anharmonic corrections are important for understanding the real energy levels in an actual molecule as opposed to a simple spring model. So to get started on the experiment, this is now over on the experiment handout, and the beginning pages here just kind of go through some of the equations that we were introducing. One term that I didn't introduce on the previous video is this equation here, equation 5, is the 0 point energy. So if you notice the bottom of the curve at V equals 0, that the energy is actually not equal to 0. So the energy of 0 would be at the bottom of the potential well. Well, all bonds are going to have at least 1/2 h nu of energy within them. We call that the 0 point energy. So 1/2 h nu is how much higher the starting point is. And then V equals 1 according to the harmonic potential. So omega E V plus a half, so V is 1 plus a half, that'd be 3/2 h nu. So each energy level, according to the harmonic model, is just h nu. So we start at 1/2 h nu, go up another, that'd be 3/2 h nu, V equals 2 would be 5/2 h nu. And so then if you imagine making the anharmonic correction, where you have this minus omega E xe V plus a half squared, then the 1/2 h nu would be then minus, plugging in a 0, so this would be minus 1/4 omega E xe. If you go up to the next energy level, plugging in a 1, so that's going to be 3/2 squared, so that's 9/4 omega E xe. If you go up to 2, just plug in a 2 here, so 2 plus a half is 5/2, so that'll be 25/4 omega E xe. So these are sort of correcting for that first anharmonic correction to really come up with the energy level being a little bit lower than we're predicting it with the harmonic model. Then we see here some terms that relate the frequency to the force constant reduced mass, like we spoke about, and then relating the nu tilde. The nu tilde is a symbol that I use in the handout to signify a frequency, but in units of inverse length. So we're just relating that to an inverse wavelength, because that's an inverted wavelength unit, and then relating that to the speed of light. So if you recall, the speed of light is equal to lambda times nu, and so then if you're relating a 1 over lambda here, so if you divide both sides by lambda, then you're going to have that equal to the frequency divided by the speed of light. So just coming up with a relationship between the wavelength and a frequency unit. And so then the first part of the experiment is going through N2, calculating the vibrational frequency in hertz and the force constant K in Newton meters. And so for N2, you're given the fundamental frequency in wave numbers. And so what we have to do is come up with a relationship between the inverted wavelength unit for the vibrational frequency, perhaps convert this over to an inverse second, so convert that to a true frequency unit, and then you can use the relationship between nu and then 1 over 2 pi times K over the reduced mass. And then remember, we're talking about nitrogen 14, the most abundant isotope of nitrogen is nitrogen 14. So look up that isotopic mass specifically for nitrogen 14. It's slightly different than the listed mass of nitrogen on the periodic table. So apply that mass when you're solving for the reduced mass of the bond. And then as you proceed through the activity, you're then going to try to compare for N2 the frequency, force constant, and then also to the dissociation energy. You could look up for nitrogen on the NIST webbook. Perhaps that'll be a separate video where I go through how to use the NIST webbook, but you can pull out some of these fundamental constants for N2 and be able to solve for things like the dissociation energy. Now, one thing I want to mention now is you'll see a DE in this experiment, and you'll see a D capital E. These are two different units. This is what we're going to call a distortion constant. We'll go over what that is later. And then D capital E is dissociation energy. So I just wanted to bring up that there's two units that look similar to the DE that have some slightly different meanings associated with them. Okay, then a second part of this handout is going to go through looking up the harmonic and anharmonic potentials, using them to solve for the vibrational energy of a molecule and relating that to the fundamental vibrational frequency. So I think that's probably good for this video here, so we'll stop at this point. We'll pick up in the handout with a later video.